So quite often we want to do something to an entire list. For instance, we might want to replace every item in the list by some derived value f of x. So we would write a loop as follows: for every x in L, replace x by f of x. Now we could write a function to do this, which does this for different lists and different values of f. So we could say define apply list, which takes a function f and a list L, and for every x in L, it just replaces x by f of x. And since L, a list is a mutable item, this will update lists in the calling function as well. So Python has a built-in function map which does precisely this. So map fl applies f in turn to each element of L. Now, although you would think that if you take a list, say x1, x2, and you apply map and you get f of x1, f of x2, that the output of map should be another list. Unfortunately, in Python 3, and this is another difference between Python 3 and Python 2, the output of map is not a list. So you need to use the list function like we did before. So you need to say list of map fl to get a list. And you can, however, use the output of map directly in a for loop by saying for I in list map fl, or you can even say for I in map fl, this will work. Okay. So you don't need to use the list notation if you just wanted to index in a loop. But if you want to use it as a list, you must use the list function to convert it. And this is pretty much what happens with functions like range and d.keys and so on. So these are all things which gives us sequences of values. These sequences are not absolutely lists. They can be used in for functions. Okay? But if you want to use them as lists and manipulate them as lists, you must use list to convert them from the sequence to the list format. Another thing that we typically want to do is to take a list and extract values that satisfy a certain property. So we might have a list of integers called number list, and from this we might want to extract a list of primes. So we start off by saying that the list of primes we want is empty, and now we run through the number list, and for each number in that list we apply the test: is it a prime? If it is a prime, then we append the list to our output list. So we start with the list x1, x2 and so on, and then we apply the test, and some of them will pass and some of them will succeed, some of them will fail. Okay? And at the end, wherever the things pass, those items will emerge in the output. So in general, you could write a select function which takes a property and a list, and it creates a sublist by going through every element of the list, checking if the property holds, and for those elements which the property holds, appending it to the sublist. So the difference between select and our earlier map function is that property is not an arbitrary function. It doesn't manipulate L at all. All it does is it checks whether a property is true or not. So property will be a function which takes an element in the list and tells us true or false. If it is true, it gets copied to the output. If it is false, it gets discarded. So there is a built-in function for this as well. It's called filter. So filter takes a function p which returns true or false for every element, and it pulls out precisely that sublist of L for which every item in L which falls into that sublist satisfies p. So let's look at a concrete example. Supposing we have the list of numbers from 0 to 99. We want to first pull out only the even numbers in the list. So that's a filter operation. And then for each of these even numbers, we want to square them, right? So here we take the even numbers, right, by using the filter, and then we map square. So then we get a list, and then of course having got this list, then we can add it up, right? So the sum is not part of this function, but we want to first extract the squares of the even numbers, and that can be done using a combination of filter and then map. So filter first gives us the even numbers, and then map gives us the squares, and the square is defined here and is even is defined. So there is a very neat way of combining map and filter without using that notation. So let's get to it through a more simple mathematical example. So you might have studied in school from right angle triangles that by Pythagoras' theorem, you know that if x, y, and z are the lengths of the two sides and the hypotenuse respectively, then x squared plus y squared will be z squared. So a Pythagorean triple is a set of integers, say 3, 4, and 5 for example, such that x squared plus y squared is z squared. 3 squared is 9, 4 squared is 16, 5 squared is 25. So let us say we want to know all the integer values of x, y, and z whose values are below n such that x, y, and z form a Pythagorean triple in this sense. In conventional mathematics notation, you might see this kind of expression. It says, give me all triples x, y, and z such that, so this bar stands for such that x, y, and z all lie between 1 and n. And in addition, x squared plus y squared is equal to z squared. So this is, in some sense, where we get the values from. This is an existing set. We have x ranging from 1 to n, y ranging from 1 to n, z ranging from 1 to n. And we put together all possible combinations. Then we take out those combinations which satisfy a given property, x squared plus y squared equals z squared. And those are the ones that we extract out. So in set theory, this is called set comprehension. Okay? This is a way of building a new set by applying some conditional things to an old set. And this is also implicitly applying a kind of a tripling operator. It takes three separate sets, x from 1 to n, y from 1 to n, z from 1 to n, combines them into triples. Right? So there is a filtering process by which you only pull out those triples where x squared plus y squared is z squared. And then there is a manipulating step where you combine them into a single triple x comma y comma z. But in general, the main point is that you are building a new set from existing sets. So what Python does, and many other languages also from which Python is inspired to, is allow us to extend this notation to lists. So this actually comes from a style of programming called functional programming, which for where this kind of notation is there, and Python has borrowed it, and it works quite well. So here is how we will write our earlier thing, which we had said, the squares of the even numbers below 100. So earlier we had given a map filter thing, right? So we had said we would take a range and we would filter it to this even, and then we would do a map of square. So in Python there is an implicit perpendicular line below before the for from the set notation. So it says take square of x for I in range 100 such that is even of x. Right? So we have here three parts. So we have a generator which tells us where to get the values from. So remember that list comprehension or set comprehension pulls out values from an existing set of lists. So we first generate a list. In this case, the list range 100. But we could use another list. We could use for I in any L, just like a for. Then we apply a filter to it. Which are the values from this list which we are going to retain? And then for each of those values, we can do something to it. In this case, we square it, and that will be our output list. Right? So this is how we will generate a list using map and filter without using the words map and filter in the thing. We just use the for the generator, if for the filter, and the map is implicit by just applying a function, the output of the generator and the filter. So let's go back to the Pythagorean triple example. We want all Pythagorean triples with x, y, z below 100. So this, as we said, requires us to cycle through all values of x, y, and z in that range. So it's a little bit more complicated than the one we did before, where we already had a single generator, all the values in range 0 to 100. So it's simple enough. You write it with multiple fors. So you say I want x comma y comma z for x in range 100, for y in range 100, for z in range 100, provided x squared plus y squared equal to z squared. So that's written with the if. Now, just to fit on the slide, I have split it up into multiple lines, but actually this will be a single line of Python code. So in what order will these be generated? Well, it will behave exactly like a nested loop. Imagine we had written a loop in which we said for x in range 100, for y in range 100, for z in range 100, do something. So what happens here is that first a value 0 will be fixed for x, then a value 0 will be fixed for y, then 0. So the first pair triple that comes out will be 0, 0, 0. Then the value of z will change. The innermost loop changes next. So the next one will be 0, 0, 1. So this is x, this is y, this is z. So in this way we'll keep going until we do 0, 0, 99. So when this reaches 99, then this for loop will exit and we'll go to 1. So I'll get 0, 1, 0. Down to 0, 1, 0, 199 and so on. So the innermost for, so z will cycle first, then y, and then x will cycle slowest. So just remember that. So let's see how this works in Python. So let's first begin by defining square. So square of x is return x times x. Then we can define is even of x to check that the remainder of x divided by 2 is 0. So we have square 8 for example, 64 is even, 67 should be false, is even, 68 should be true, and so on. So now we have list comprehension. So let us look at the set of square x for x in range 100 such that x is even. So we see now that 0 is there, so 0 square, 2 square, 4 square, 6 square, and so on. So this is our list comprehension. Now let's do the Pythagorean triple one. So we say we want x, y, z, okay, for x in range 100, y in range 100, for z in range 100. So this is our three generators, with the condition that x times x plus y times y is equal to z times z. And now you see a lot of things which have come. In particular, you should see in the early stages somewhere things which are familiar with like 3, 4, 5 and so on. But you also see some nonsensical things like 404. So we should probably have done this better, but we won't worry about that. But what I want to emphasize is that you see things like say so you see 0, 77, 77, which is a stupid one. But let us say, for instance, you see 3, 4, 5, right? So we saw 3, 4, 5 somewhere. So 3, 4, 5. But you will also see later on 4, 3, 5. Now one might argue that 3, 4, 5 and 4, 3, 5 are the same triple. So how do we eliminate this duplicate? So we can have a situation just like we would have in a for loop, where a later loop can depend on an earlier loop. If the outer loop says I goes from something to something, the later loop can say that j starts from I and goes forward. So for instance, we can now rewrite our Pythagorean triples to say that x is in the range 100, but y doesn't start at 0, it starts from x onward. So y is never smaller than x. And z is never smaller than y, so z is also never smaller than x, because y itself is never smaller than x. And this version will actually eliminate duplicates. So here is our earlier definition of Pythagoras, where we had x, y and z unconstrained. So what I do is I go back and I say that y is not in range 100, but y is in range x to 100, and z is in range y to 100. And now you will see a much smaller list, and in particular you will see that in every sequence that is generated, x is less than equal to y is less than equal to z, and you only get one copy of things like 3, 4, 5. So you see 3, 4, 5, but you don't see 4, 3, 5. So 3, 4, 5 is here. Next one is 5, 12, 30. 4, 3, 5 is eliminated. So the key thing is that generators can be dependent on outer generators. Inner generators can be dependent on outer generators. So this list comprehension notation is particularly useful for initializing lists. For example, for initializing matrices when you are doing matrix-like computations. So supposing I want to initialize a 4 by 3 matrix to all zeros. So 4 by 3 matrix has 4 rows and 3 columns, and I'm using the convention that I store it row wise. So I first store the first row, so it will be 3 entries for the first row, then 3 entries for the second row, and so on. So here is an initialization. It says L consists of something for the outer thing says this is for each row. Right? So it is something for each row. So for 4 rows, 0, 1, 2, 3, I do something. And what is that something? I create a list of zeros of size 3. So each row j from 0 to 3 consists of columns 0, 1, 2, which are zeros. Okay? So this will actually generate the correct sequence that we saw that we would need to initialize such a matrix. So here is that list comprehension notation for initializing the matrix. So it says for every j in range 4, right, we create a list, and that list itself has 0 for I in range 1. And if you do this and look at L, then correctly it has 3 zeros and 3 zeros and 3 zeros 4 times. So these are 4 rows with 3 columns of zeros. So suppose instead we split this initialization into 2 steps. We first create a list of 3 zeros called 0 list, which says 0 for I in range 3. So this creates a list of 3 zeros. And then we copy this list 4 times from the 4 rows. So we say the actual matrix L has 4 copies of 0 list. Now we go and change one entry. Say we change entry 1 in row 1. So from the top it's actually second row. So it's the second row, second column if you want to think in normal terms. So we take the list 1, which is the second list. Now what you expect is the output of this. So here we have the 0 list, and then we say L is 4 copies of 0 list for j in range 4. So superficially L looks exactly the same. Now we say L1, 1 is equal to 7. And if we look at L now, we will find that we have not 1 7 but 4 copies of 7. So this is apparently something which we did not expect. So the output after L11 is equal to 7 is 070, 070, 070, 070. And why is this happening? Well, that's because by making a single 0 list and then making 4 copies of it, we have effectively created 4 names for the same list. So whether we access it through L0 or L1 or L2 or L3, all 4 of them are pointing to the same 0 list. So any one of those updates would actually update all 4 rows. So if you want to create a 2-dimensional matrix and initialize it, make sure you initialize it in one shot using a nested range and not in 2 copies like this, because these 2 copies will unintentionally combine 2 rows into copies of the same thing, and updates to one row will also update another. So to summarize, map and filter are very useful functions to manipulating lists, and Python provides, like many other programming languages based on functional programming, a notation called list comprehension to combine map and filter. And one of the uses that we saw for list comprehension is to correctly initialize a 2-dimensional or multi-dimensional list to some default values.